So we continue today with Fortran again. So I'm just go. Next part is on how to structure your code. So if we look at smaller projects, usually you don't have to do anything special to structure. You have perhaps a few source code files and some functions. But when you get to a larger project and it grows, you need to divide up your code in a way that you can maintain the code. And in Fortran 90 and 95 above, modularization is the key. So and you should use the module structure that's available in Fortran. And modules provides you not only with a way of modularizing your code, but also a way of using a better way of calling your subroutines. That you can call them with. You don't have to send over the sizes of arrays. You can use the array features that I showed you last time. So this is an example of how you could divide up your source code. So you have your program, your main program, and then you have a number of modules for different things. For example, one module could be for providing input data to your code, or reading and writing data. You can have one that is, for example, in structural mechanics, again, a finite element module with all your algorithm for finite element code. You have a special module for solving your, running your simulation, solving your problem, and you have a module for output data, writing your results to disk. And then perhaps you have something called the routines that you use in every module. And that could be a utils F95, where you provide all your, it could be stuff that you use in multiple things that are not kind of, you can put in a certain module, but you need it in several places. And you can have that module. So in this case, we have a program that uses these modules, and every module here uses the utils module. So you have the module dependency. So if you look at, make it darker. So here we have our utils module here. We have a FEM module and we have a program. So you can see in the program, we call it stress, and we use input data. So this is very similar to the import statement in Python. So this is a Fortran module. You use it based on the use statement. And then all the subroutines that are public, all variables become available in this. Then you have output data, FEM, and solve. So now all these subroutines are available in your main program. And then you can see here I have my module FEM. So module starts with a module keyword and module FEM. And then this module can use utils. And that is this one here. Utils is not, in this case, you can't use the functions in utils in the main program, only from within inside. You could, of course, have utils here as well if you want. But if you want to map the tree I described, you have to do it like this, use utils, and then we have module utils here. So a little bit more about subroutines. So something that was new in Fortran 90 is that you can have procedures or subroutines can take subroutines as arguments, just like we did in Python. So you can pass a subroutine over. However, it's a bit more complicated. You need to declare the format of your subroutine that you want to pass, so that the main program knows what kind of subroutine to provide. So you have the same exact calling convention. And then you define the type here in the specification part. You can't use internal procedures as well. You need to have other things. So here's an example here. I have a module utils here, and I have a function here called myfunc, which is something I want to be able to replace. And here you can see here that I have here is a input called func. And you need to declare that for the subroutine here. So in this case here, you define something called an interface that basically is a declaration for a subroutine. So it tells the compiler, I expect a function of a certain type. So in this case, I expect a function of real8 with the name funcx, and it returns as an input variable x, and it's going in here. And then then you call here, and then you can, in your main program, then you can you call your own function here, providing, just like in Python, you provide the name of the function here, and that would be called. But the important stuff is that you need to declare the interface here in your subroutine. The subroutine that want to use the function, you need to define the interface here. And when you declare another function you want to pass over, you need to make sure that it has the same interface. So that enables you to do some powerful stuff in Fortran as well. Another nice thing that is very similar to what you have seen in Python. So in Python, you can have keyword arguments. So you can give names of an argument instead of providing a certain order. And this is a way of also reducing the number of parameters you need to call a function. Sometimes the function is very generic, and you have 10 of arguments, but all of them could have default values. And a way of reducing the complexity is that you have optional arguments that you don't have to provide. And there is an attribute you can have when you declare that the variables coming into a subroutine. You add this optional attribute here. That means that the user doesn't have to provide that argument, but you can also test for the presence of an option if the variable is available in the call. So here is an example. We have 3 parameters here to our subroutine. The first argument here is non-optional, so it has to be given. Then we have 2 additional arguments here with optional attributes. So you don't have to specify those if you call this subroutine. But you need to be able to, so subroutine needs to be able to check, is this subroutine called with this argument? Then you can use the present function here. So if present flavor, then you do something like this. Otherwise, you do something else. So this way you can actually, so if it's not given, you can set, for example, a default parameter for that argument and calculate with that. But the user can choose if he wants to call with only a single argument or with all 3. It's also possible to specify, so if you don't say anything, you have to specify the arguments in order. So either number and the flavor, or number, flavor, and topping. If you want to only specify topping, you have to give a name to that argument. So that's very similar to what you can do in Python. You tell it you want to have topping equals to 3. But then you specify, I have specified the 3rd argument, but not the 2nd. Another thing you can also do is you can have multiple subroutines with the same name, depending on the data type it is called. And then you can declare an interface defining what data type, and the user, if you can call, you can have multiple subroutines with different names that you call with a single name, and depending on the data type you provide, the different subroutines will be called. I think it's better to do an example. So here I have 2 functions here. I have an I function here, which has an integer parameter coming in. This here, I think I forgot to mention this. This is a way of an attribute that tells the compiler that this variable goes in. You can't change this parameter inside here. If you do it, you will get a compiler error. You can also do out. Then you can change the inside here. You can have in out as well. So this is a way of making sure that some arguments coming into a subroutine are not assigned by mistake. So this is an integer. Then I have a other function here. It should be D function. Oh, it should be real. This should be an R function here. Here, I'm sorry, I'm confused. This one here, procedure real. So this is a floating point function. I'm going to do some other operation, and then I'm going to combine them so that I have only a single function that I can call. So if it's an integer, you can call this one. If it's a floating point, we call this one. Then you can declare in the module declaration here interface function. So this is the function I want to have different arguments to, and I specify module procedure ifunc rfunc. Using this, you can call function, and depending on what data type you have provided here. In this case, I have data type A equals to 42, and I have B equals to 42. This is a floating point, but I can call this here, the name function here, and determining of the data type here, it will select either ifunc or rfunc. Another cool feature is that you can overload operators in Fortran as well. So if you want to do a matrix library, or you want to have some kind of library that does some algebra or some algebra, you can define an operator and for different data types. So in this case here, I want to define a vector data type, and I want to define the addition operator for adding vectors together. So this only works on derived data types. So it's only your own data types you can define overload operators. So in this case here, I have a vector here that is a floating point of 3 components, and I define the operator plus here, module procedure vector plus vector. So I have to define a subroutine for adding vectors together. So in this case, the function returns the vector, and it takes 2 vectors as input, and then I do my operations here. But the cool thing is now that you can, I've added my module vector operations. I defined 3 vectors like this, assign my components, and now this works with vectors, so you can add vectors together automatically. And this plus operator here is overloaded, so that will call the vector plus vector subroutine. So in this case, you can overload all of the operators in Fortran and actually do your own algebra for your own data types, which is quite cool, I would say. You can also in your module control visibility of variables by using the private and public attributes. And that you can hide both variables and also subroutines. And by default in Fortran, everything is public. So if you put anything in a module, it will be public. So you need to explicitly tell it should be private. So here I have 2 variables, visible and invisible. One is called public here. Not necessary to do this. This is by default. I have a private function. I have a public function. So I can implement the private function and a public function here. And the thing is, this is enforced on a compiler level, so it's actually not possible to compile a code and call the private routine. The compiler will say this is not found. So this is an example here. So I have a program here. I use my module, call public function, no problem, no errors. Use my module, I call private function. And you can see here when I compile, it complains here, undefined reference. It can't even find this private routine. It's hidden, and you can't compile it. So this is a way of protecting your implementation from the user of your libraries. So for example, when you use private functions, for example, if you have a module that implements some larger algorithm, so you can perhaps have smaller routines that you don't want to provide as an interface for the users. You want to provide it internally, use it internally in your module, but not outside. Then you can just add private to your functions, and then it is hidden from use. Another concept that is new to Fortran 9 is the possibility to use pointers. And so in most cases, you don't need to use pointers. You can kind of work without it, but it enables you to do things like linked lists, binary trees, a different way, and it's not implemented in the same way as in C. So pointers in Fortran are strongly typed, and there is a mechanism of assigning a 0 pointer and removing a pointer to when you're using them. So it's more strict than in C and C++. So a pointer is a reference to a variable, similar to what you made in Python, that a variable in Python is a reference to data in memory. But in this case, it's a reference to a variable. So if you need to have a declared variable to be able to point to it. It's strictly typed, and the pointer target must have a target attribute. So if you want to point to something, you need to use the target attribute on the things that want to be pointed to. So it's also for not favorite, so you can't point to anything. Using pointers, you can, for example, return allocatable arrays from procedures. So if you allocate something in a subroutine, using the pointers, you can actually return it out. And now there is in modern Fortran, you don't have to use it for this, but this is a way of doing that. There is a separate subroutine called nullify to disassociate the pointer from a target. And equal sign greater than here, this is the pointer operator to actually associate the pointer with the target. So let's see how it works here. So I have here so I have one allocatable array, A, and you can see here, I want to point to this A at some point. So I add the attribute target. I tell the compiler that this is something you can point to. Then I have two pointers here, B and C. You can see here you need to declare the type here. So I have the same type as A, but I have an attribute pointer. So these are, when we allocate them, they don't point to anything, so they are illegal to use. I allocate my A array. So now this is a 20 by 20 array, and memory has been allocated. I can assign the B pointer here to point to A by using B points to A. So now B points to the same memory location as A. And then you can use the same operations for querying this. Now it works like a normal array. So there is no difference in use of this B here. So B can be used just like A. And it's actually a reference to A. So if you change anything in B, A will also be changed. Then here I have here create an array function here, D. So in this case, I have a dimension : pointer D. And then I allocate inside here. Because there's a pointer here, when the reference you put in to create array will actually be assigned. The C will point to this array. So when I run this here, it will return the size of the allocated array inside. Then I can do deallocate C, same thing, and then that will be destroyed. And before you, when you don't want to point B to something, you can point it to the function now parentheses. So now B doesn't point to anything, and it's again not legal to use. If you try to use this, you will get a program with segmentation fault and crash. Yeah. So if you try to use this one here in Windows, all Windows systems, you will get an access violation. So because you access memory where you're not allowed to access. So there's nothing preventing you from accessing an associated pointer. You'll probably get some warnings from the compiler, at least if you compile it, but you can do it. So I want to go through a bit about more advanced I/O functions in Fortran. List directed I/O. So this is the normal way of writing things to disk. As I said before, Fortran will automatically do the conversion to and from variables. So if you write a variable to disk, it will convert it from a floating point to a text representation. And you do that is done in the write statement. And when you write out your variables, they will be separated with space and blanks in the files. And if you write out complex numbers, they will be surrounded with parentheses. Strings will be also, you have to have either single apostrophe or double quotes when you output them. And then if you want to read back, it has to be the same format. So you can't have your own format. It has to be the same format if you want the read statements to work. So here I have some variables I've declared here, string, boolean, and a complex value here. If I open the file here, this is if you already have a file on disk, you can have a option here that I wanted to be able to replace. That I don't want to create a new, it should be replaced. So this is one way of telling Fortran that I want to overwrite any file on disk. So write IV, that is the unit for the file. Then I just list my things here: A, comma B, comma string output here, topping, comma C. And you can see here that I need to specify the apostrophes here on top of this to be able to read it back again. But in the file, it will be spaces between the variables. But then you read it back again, same way, read A or B, string, topping, and C. So let's see what it does. So this is what it wrote out to disk. Integer, floating point, hello string. And you see here where I need those things here to be able to read it back correctly again. Logical value will be written out as either T or F, true or false. And a complex number, parentheses, 1.000, 2.00, and then parentheses. This can be read back again with a read statement. So there has to be an equivalence here between reading and writing. Then there's another way of writing to this called name lists, name list IO. And here you can read from a list of named values. So it's very similar to the JSON format I described in Python. You have to define names in a name list. So this is a special reserved word in Fortran. And then the input must consist of a list of name value pairs separated with commas. So like this, name value, backslash. So you start with and sign and ends with a slash. And you can contain arrays, so name can be an array, 1, 2, 3, 4, 5. And you can also, Fortran can also write name lists to disk. So here's an example here. I have defined some variables here. And I have defined a name list food. This consists of number of eggs, liters of milk, kilos of butter, and list. So what happens then is you can open a file and you can say, I want to read using this name list. So I expect the data to be in the name list format. So it should be these variable names. The same thing, I can write it again to disk using the name list food. And it will use the variables that are defined in the name list when writing to disk. So let's see if we can do an example. So this is what I'm running now is the development environment that I hope that you have been able to configure. Let's see here if I go to list. So I'm going to run this now. Change. List. Needs to be, so the problem is that I don't have the file, so I have to create that first. So I will do wrong language. So we'll just do list. Next. Kills the button. So So nothing happened here, so let's see where we are. Now I can see I have a food.txt here, so if I open this one, you can see here that it wrote this. So this is the name list. It has number of x1, liters of milk 2, kilos of butter 4, and then lists here, and it just lists this, writes it out to disk. And then I can do the same thing here. I can read it back again. Yeah, you can see here that I printed out 1, 2, and 4 here. So I could read them back in the same format. So just having this, you can write your own files here, just like you have JSON files. You specify the variables here and the values of those, and then it will read those to this. So you can see here that number of eggs, comma, liters of milk, comma, kilos of butter, comma, list, and then you have comma separated values here for this, and then you end like this. So this way you can define input files in Fortran with named variables, and it will automatically read. You don't have to do your own file format. You can do it using the named list definitions. And the third way of writing to disk is using unformatted I/O. And then what that means is that sometimes the text representation is not the most efficient thing to write to disk. If you have large amounts of data or you want high precision, you need to write your floating point variables in binary form. And that you can do by using the same statements here, read A, write B, and those will be written as in binary format to disk. However, you should be aware of that writing to binary files from Fortran depends on your platform. So depending on the compiler and platform, the format is not guaranteed to be identical between systems. So use binary files for temporary files or scratch files. So for example, for writing down the state of the simulation, you can write down everything as a binary file. And if the simulation terminates, you can restart it and you can read back the variables again in binary form. There is also a way of, so if you want to write binary form, you can also have something called direct access file. That means if you have your file is structured in records, you can access the different records randomly. And that requires you to define a set of equal sized records in your file. And then you can jump between those records in a random way. Also, if you change the record type, you can't read it back from file again. It requires the exact same record again. And also to be able to determine how large records to write, you need to use the function inquire here to actually specify, to query the size of the record. So I think we need to have an example here. So here I have I want to store bank accounts. So I have a account type here. I have a name of the account holder and I have a balance here. And then I have defined just two accounts, account A and account B. And I define a variable record size where I want to store the size of the record. So the first thing I need to do before using random access files is to inquire about the length of the record size. But you need to know how big is this on disk. So then you do inquire IO length record size. And then I specify which record to query. So in this case, I just take account A. Then this will be assigned here and given the size of the record. Then I just assign my two records. This is a very academic example, but assign values to them. Then I open my file here, bank that, access direct here. That means the tells the compiler we want to access the file with random access. And the record length is record size. Status replace the file. Then I write my account A. This is record 1, record 2. So you can actually specify where to write it. And then I close my file. So what next? Yeah, so you need to find your things again. So when you open a direct access file, there is something called a file pointer, which it can be compared to a cursor in a Word document. You can move the cursor back and forth. And the unit of movement is the size of the record. So you can have backspace units to move the file pointer back. So if you read something, the file pointer moves forward one record. Here you can go back again one record. Rewind, that means that you go back to the start of the file. And you can also move the file to the end of the file. So, for example, if you want to add something to the end of the file, you can do end file unit, and it will move the pointer to the end, and you can continue adding records to it. But it can go completely back and forth. Okay, I thought I had an example of that. Yeah, but there should be examples in the source code, the library that you get. So when you're reading and writing files, things can go wrong. You can, when you read from or write to disk, your quota, for example, the disk could be full. And somehow you need to be able to handle, or most programs should handle errors in a nice way. And there is an error attribute that you can set to a certain label in your code. And if an error occurs, it will jump to this location. And you should, well-behaved program should do this when you read. So you tell the user that something went wrong. So in this case here, error 99. And this is actually the only place in Fortran where you use line numbers. But the only thing is when you have error handling. So it's compared to the try except things in C++ or in Python. But here we use line numbers. When there is an exception, it will jump to line number 99. In this case here, if there's some error opening the file, it will go to 99. If there's some error reading, it will go to 99. Closing, 99. You can have, of course, different labels here as well for that. So here you can handle error. So now we go through some of the new features of modern Fortran. They are not new anymore, they're a couple of years old, but there are still things that have been added in Fortran 2000 and forward. So there is, so I told you before that to allocate things inside a subroutine, you need to use pointers. But no, not anymore. So if you declare allocate array as an argument in a subroutine, you can actually allocate it inside the routine, it will go out allocated. Before it was, if you have an allocatable array, it was deallocated inside the subroutine. But if it's an argument, it will go out again. So here's an example here. I have an array here, which is not allocated here. So it's just declared, undefined. I call create array here. Go down here. And you can see I have declared real allocatable array here. It's going out. I allocate it inside here. And now I can use it here as well. So this is a way of pre-initializing variable. For example, you can have a subroutine called once, for example, we have in Python. And that will create an array with once inside it. But you still need to deallocate. So it doesn't take your responsibility for actually deallocating your variable as well. So this is a new feature here. It enables you to do a lot of cool things with subroutines. This is also something, so the first thing they did was add this feature to the subroutines, but you can also do this as a function. This is even more cool. So you can actually do something like this, create vector, so you can return out an allocatable array. So this should be this. So inside your function here, dimension colon create vector, it will be, so you pass in the size of the array you want to create, and then you can allocate create vector, and that will be a return out from this function. The reason I have this because I couldn't, I think I had an example of this in the code. this is the correct syntax every time. It's a fairly new function. I know that in some examples it was added to the standard, but I couldn't use it. There was no compiler to do this, but this is the way to do it. So I have A here, A equals to create vector, and A will be created inside here. So you can create your own allocatable routine for allocating. So this could be, for example, ones that could create an array of identity vectors. I'll change this slice later. Also something that couldn't be done before. So if you have a user-defined type, before you couldn't have allocatable arrays inside the type. But this has changed now, so you can, in your type, you can have integer allocatable content here. So you can actually user-derived types with allocatable components in the data structure. You could, as I said before, you could use pointers before. So you could have a pointer inside a data in a derived data type, but now you don't have to use pointers to do this. You can have an allocatable array inside your derived data type. Another thing that has been added to Fortran is the ability to divide up modules. So suppose you have a large module, it grows, you add functions to it, and it grows and grows, and all of a sudden it's 3,000 lines of code. But you still want it to be a single module. So what you can do in Fortran 95 and above is you can create submodules. So you can divide up source code in the same module in several source code files, so that you can easily handle larger modules without having a super large source code file. So this is an example of this. So I have module points here, and I have a submodule here, points. And so this is a submodule of points, and I can continue adding stuff here. And this could be a separate source code file from this one. Another thing that was added later Fortrans is the ability to interoperate with C and C++. So one problem, as I said before, that the data types are a bit undefined in Fortran. That depends on the system architecture. So they have decided to add definitions that you can use when you declare variables that are guaranteed to be C compatible on that platform you're compiling. And this is important when you want to interface with C libraries, you want to use C routines in some way, provide interfaces to C programs. You need to be able to declare your Fortran code in a way that C understands it, or declare your C routines that you can declare use them in Fortran. So there is a new module called ISO-C binding, and that contains all of the C data types mapped to the corresponding Fortran types. Sounds kind of simple, but it's really important. So for example, here you can use, if you call this module here, you can declare integer C int. So this will be guaranteed to be correspond to a C integer. Same thing is C float, but there's a C floating point, C double corresponds to the double data type in C. And of course you can add this as suffixes here as well to guarantee that you get your scalars here for the correct data type. Another thing that is problematic when interoperating with C and C++ is that C, by default, scalar values are passed by value. So a variable is passed not by the reference to the variable, but the actual value of the variable. And that is not the case in Fortran. Fortran, by default, has everything by reference. So if you send a parameter list over to Fortran, the subroutine can modify because all variables coming in are references to the actual variables. But now, with the later versions of Fortran, you can actually add an attribute called value to your variables coming into subroutine to indicate that this variable should be passed by value and not by reference. And that enables you to declare functions in Fortran that you can link directly with C, because you can map them directly. So a subroutine in C can be mapped directly to Fortran and called from Fortran exactly like we wanted to. Another thing which has been added to Fortran is the ability to implement object-oriented programs. So it looks a bit different than Python, but it's very similar. So in this case here, I have this is a class. There is no class to the declaration. You don't. That's when you define a class in Fortran, you use it, you create it like a derived data type. So in this case here, I create a new derived data type, but there is a contain section here, and in the contain section you can declare the methods that should be applied to the be included in the class. And then you can declare your object here or instance here by using class here. So class is used when you want to create an object. Let's see here how the So this here, the system corresponds to the self in Python, and then you can add things to this, my value, this here, just like you do in Python with the self operator here. So this is the implementation of the class, and here you can declare your class. Here's a class M type X. This is an instance of the class M type, and then you can do call X %write6 X %reset. And you can allocate those on you can declare a class M type comma allocatable here and actually allocate it as well dynamically on the heap. So now Fortran is a fully object-oriented language. Another thing that has been really strange that it hasn't been added to the standard is access to the computing environment. I talked to you about in Python you can access environment variables from the system by the built-in end of the dictionary. In Fortran, there has been no standard way of actually doing this until now. So there is now they added functions you called get environment variable to access environment variable. You can also access the command line arguments here using command argument count. You can get command arguments here as well. This has not been possible before. There has been extensions for different compilers that have been implemented this, but it has not been part of the standard. So now this is part of the standard, enables you to create more efficient programs that interact with the environment in better ways. So we take a 10 minutes break, and I will look at the Qt Creator as a Fortran environment after the break. So the final part, I would go through the development environment that you can use as well. It's perfectly fine. You can use Fortran on the command line if you want. That works. But I have implemented some plugins for the Qt Creator, which you can use to compile Fortran code. So if you download and follow the instructions I provided, you will get the Fortran compiler with the environment. And then adding my plugins, you can use. You can create Fortran projects directly with the Qt Creator. I first wanted to show where you can find, for example, on Windows, where the settings are. So it's also documented in the documentation for this. So there is a folder in Windows called App Data, and where the program stores their configuration files. And when you install Qt Creator, there is a folder called Qt Project. And there is a folder called Qt Creator. And when you download my extensions, you download this file here. And if you open this file, it contains a folder. And these are the files you need to copy to the directory here. So let's go back here again. In this directory here. So if you copy them, just paste them in here. They will add the plugins directories you require for the code. So if that is installed, you can go back to Qt Creator. And if you want to create a Fortran program, you go to File, New Project. And there you can see there is a lot of different applications you can create. But on non-Qt projects, there are several things you can do. You can do, there's plain Fortran application. There's a Fortran F2Py extension, which I will discuss in the next lecture. This is a standard Fortran application which you can create. So you press choose, then you can give it a name. So my Fortran code. And you can see here it will be created in this directory here. And press next. Then it will ask you for a build system. And that is also something we'll go through in the following lecture. So you just select CMake here. Keep the default, press next. Make sure that the MinUV here in Windows is selected. You press next and finish. Then you can see here it creates a standard Fortran code with a really simple implementation of hello world. So you can see you have a program my Fortran here, contains section and program, and then a print statement here. And if you want to compile it and run it, you can press the play button here. That will compile the code. And if you want to see the compiler output, you press the compiler output section here below. So application output is where the program will print its output. Compile output is compilation code. So if, for example, if I forgot something here and I want to compile it again, you can see here that the compile output here shows the error here. So what is that? Unterminate character constant beginning at 1. So this is so there's missing apostrophe here. And then I can, so this play will compile and run. The hammer down here will only compile. So you can see it built. It's also possible to debug. So if I, for example, do so if you press outside here in the section here with the line numbers, you can set the breakpoint. And the breakpoint is when you run the code, the development environment will stop there, and you can step through the code. And to debug your code, you press the play button with a bug on it. And you can see here now the code stops here. There's an arrow here at the red mark. So it's here in the code. And you can also see here that here is the control panel for the debugger. And here you can see where we are. So this is the call stack, it's called. So it's the routines leading up to the main call here. So you can see this is from the system here. And this is the main call. So we are in the main routine. And here you can see also, see if I can move my ruler here. Here you can also see the variables that are declared. And in this case here, argument 1 here. The command line arguments. So if I run this code, I can step. There are several controls here. continue will continue to the next breakpoint. So if I run it again, it will continue and stop again here at this point. There is also stop that will stop the program from debugging. There is step over here, which will step one step in the code. And if you have a subroutine, it will go into the subroutine as well. So this is the step into. Go into subroutine. If you're into subroutine and you want to go out, you can step out. It will go back to the main routine again, or the calling routine. So if I go step over here, you can see it stepped down to the print statement. Then if I do it again, and you can see that you can add application output here just to make it even more confusing, the layout here. So you see here, it printed one. I continue to step here, printed two. And here you can see that it shows you the variables that are in the code. So in this case, I have I here, and the value is 4, and you can also see what kind of data type it is. I can remove a breakpoint by just clicking on it, and then you press continue here, and it will run to the end. So debugging is quite useful when you have problems in your code and you want to see what is going to happen in the code. You can, for example, if I declare here real, now I do something you shouldn't do, real 8 here. I do an array. And I do, I run this code here, I do A11 equals to and we will stop here. Okay, I thought I could see. Yeah, we can see. So now I have a picture of my A variable here. And this is the result of this is, as I just declared it here, I haven't assigned anything, so it's undefined. But we can see here what the problem is with having undefined variables. So if you look at A here, you can see here that there are a lot of garbage values here inside. And that is due to that this hasn't been allocated or assigned. So if I do step over this one here, you can see here that it's set 0 here to 0.0. And if I stop here again, and if I do instead just assign the entire variable here, and then run it again. So if we go up here, you can see there is garbage here. And if I step over one step here, you can see here that the entire array was zeroed out. This will zero out the entire array. So debugging is quite useful to actually see what happens inside your variables in your code. So this is live machine code that is debugged, and it shows you the memory addresses here. So this is actually memory in your computer somewhere, and the actual values of the variables. Yeah. And then, so if you want to add a module to your project code here, you can do that as well. So you can do new file. You go to Fortran, and I want to do Fortran module file. Choose, and I see here you have to make sure that you place it in the right module here, right directory. So I call this my mod.f90. Next. And now I've created a new file from here. So how do you add this to your code? As long as your source code files are in the same directory, you should be able to build it again, and it should add this file to the source code tree. Let's see here. Okay. Okay. So now you need to. So if you add a file, you need to run CMake again. So because when you the CMake builds a project for you, and if you add a file to your existing directory, you need to do run CMake again to add a file. So if I do another module here for new file, and I do a Fortran module file. And then I do right click, run CMake here. And now you see I have two modules here. And it will also build when I build the program like that. There is also a convenience thing here that you can choose a Fortran data type constants module file. So this will actually create a module that contains some useful declarations. Data types. So this will create modules with some of these files that you can use instead of using selected real kind everywhere. You can do real kind and then real kind single position like float and C, and then different integer types as well. So if you go back to my main program here, I can do use data types. Then I declare my variables here, real kind, like this. So now I could this definition here is comes from this module here. So I hope you find this useful. You should be able to download and install this on both Mac and Windows. And I think also if you do it on Linux, you need to install the compilers, the Fortran compiler, and it should work automatically on Linux. So most of the special configurations are for Windows. The plugins and the templates needs also be this. There is a .config directory in Linux, which is also described in my course material, where you should put these files from this. Where you should extract the files from the plugins for Qt Creator. So